Let's talk about part 1 of AC bridges. As you know, this chapter is pretty big, so I will be splitting it up in many parts. Okay, let's get started. Okay, AC bridge is actually a modified version of Wheatstone bridge. Okay, in Wheatstone bridge we were using an impedance, a DC source, a galvanometer. Okay, but in AC bridge what we are doing is we are using an AC source instead of a battery and a detector in place of a galvanometer. Okay, now the applications of AC bridges are it is used for measuring purpose. Okay, measuring your unknown impedance, unknown frequency, dissipation factor, and electrical permittivity. Besides this, it can also be used as a feedback path for amplifiers and oscillators for phase shifting or filtering undesired signals. Let's talk about source and detectors. At lower frequency, we use power line supply. At higher frequency, we use electronic oscillators as a source. Let's talk about detectors. Okay, in DC Wheatstone bridge, we use galvanometer, but for AC bridges, in AC supply, there are some frequencies. Okay, based on those supply frequency, we have chosen these as the detectors. Okay, from 5 hertz to 1000 hertz, we are using vibrant galvanometer. From 250 hertz to 3 to 4 kilohertz, we use headphone, and for having a supply somewhere 10 hertz to 100 kilohertz, we use tuned amplifier detector. Okay, now we are talking about condition of bridge balance. Okay, this is your old Wheatstone bridge, this is your DC supply, and this is your galvanometer over here. Under balanced condition, no current is passing through this galvanometer, and this method was pretty effective in finding out the unknown resistance over here. Okay, and this was your condition PS equals to RQ for finding unknown resistance over here. Okay, now what we are doing is in AC bridge as well, there should be no current flowing through the detector. Okay, this is your AC bridge. Okay, no current should be flowing through this particular detector. Now the conditions that need to be satisfied are this. Okay, I1 Z1 equals to I2 Z2 and Z1 Z4 Z2. These are the conditions to be satisfied. Okay, but for finding an unknown impedance, suppose this is your particular AC bridge over here, and what we are trying to do is we are trying to find out this unknown impedance along with the magnitude and angle. Okay, so what we are doing is these two conditions should be satisfied. Okay, for finding out the magnitude, this condition should be satisfied, and this condition should be satisfied for finding out the value. When both of these conditions are satisfied, only and only then you can find the exact value of this unknown impedance. Okay, the angle is also important. The unknown impedance will have this particular format, magnitude with this angle. Okay, so both of these conditions are mandatory. Now what we are doing is finding an unknown element using an AC bridge. Okay, this is suppose your AC bridge. Okay, with having so many known, with three of these are the known impedances. This is your AC supply with particular frequency, this is your detector with current passing through it, and this is your unknown impedance. Okay, unknown element, you don't know what it is right now. So your this particular impedance over here, unknown impedance, is having this particular formula, is it is in this format, and the angle is given in this format. Okay, so what we are doing here is if the angle of theta is 0 degree, we can simply say it is a pure resistance. If the angle theta varies from 0 to 90 degree, the combination over here is R and L. Okay, if it is strictly 90 degree, then it is pure inductive. If it is minus 90 degree, it is pure capacitive. And if the value of the theta lies between minus 90 and 0, the combination is resistance and capacitance. Okay, this Z over here is actually a combination of resistance and a capacitance in case the value of theta is between minus 90 and 0 degree. Okay, this is for your AC bridge. Okay, for finding an unknown impedance and unknown elements. Okay, now we are moving on to case 1. Okay, in case your unknown impedance is inductive in nature, so okay, this is your bridge over here. Okay, this is your unknown R and L combination over here, this is your detector and the current is passing through, and this is the bridge arrangement over here. Okay, used for finding these two unknown elements over here. So for finding these R and L, these are the formulae. Okay, for finding the unknown resistance R. Okay, this unknown resistance R is given by this formula, and the unknown resistance L is given by this formula when you are using this particular bridge circuit for finding the unknown impedance. Okay, the case 2 is If your Z is, if your impedance is capacitive in nature, then you have this particular formula or this particular formula, okay, RC combination. Under balanced condition, these are the two conditions you need to keep in mind, okay. Under balanced condition, so is the case, okay. Now let's talk about sliding balance, okay. Elements not common in unknown value are selected as variables if the variable are common, more laborious and time consuming, okay. These unknown things are called the variables, okay. If you are choosing a common thing which is these unknown variables, okay, you are choosing something which is common to both known and unknown, okay. If you are choosing a common element, say you are choosing a resistance, okay, you are having resistance over here, 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 so what will happen, the bridge will take more time to get balanced, okay. And this is actually your sliding balance thing. Now what we are doing is convergence to a balance point, okay. In case you are taking that variable for balancing the bridge which is not common, okay. If suppose you are taking the L over here, okay, this is not common to any arm of the bridge, okay. So here what you are, by taking this we are having an advantage, the bridge will come to balance rather quickly, and this process over here is called convergence to a balance point, okay. This is all for part 1. In part 2 we shall be discussing from measurement of inductance.